Hello and welcome back. As promised, today we're going to do space math. We're going to apply what we know about right triangle geometry to the world around us. Literally the world, like space. It's going to be really cool. But first, I need to teach you about tangent lines. So tangent lines we've talked about tangent lines and secant lines and chords as well. We did that on Monday in our vocab video in central angles. So that's 10-1 if you need to go back and watch that again. But tangent lines and secant lines are different. They're both lines that intersect a circle, but a secant line intersects a circle in 2 points. So one of our postulates tells us that if a line intersects a circle and enters into the circle, then it also must intersect the circle again to exit the circle, and that's called a secant line. So this line here would be a secant line. As I move down, if I go through these 2 points, it's still a secant line because it intersects in 2 places. Same thing here, and it's not until we get to the very bottom that we actually have a tangent line when it goes through this green point. This is where it only barely grazes a circle and intersects it in 1 point, and is called the point of tangency. All right, so I've shown you another way of illustrating this, but I want to show you now on GeoGebra. So GeoGebra is nice because we can actually interact with it and visually see how everything is changing in real time, kind of like an animation. So on this, if we have a diameter, and this is not exactly a diameter because it's not exactly 180 degrees, but it's the closest I could do and still allow this to be interactive and not constructed and well defined by parameters. So anyway, just pretend like this is 180 degrees. So if this is 180, that's our central angle. Then our inscribed angle here is going to be half of that value, which is basically 90 degrees, right? And what's cool, which is Thales' theorem, I actually showed you on the second day of school, is that as we move this and we pick any one of these vertices, any one of the points that are equidistant from the center, right? Any point on the circle, it's still going to have the exact same angle of 90 degrees. So every possible right triangle or different lengths of the legs of a right triangle with a given hypotenuse of the diameter of the circle exist on the semicircle, has the 3 points on the semicircle, which is pretty stinking cool. Now what happens if I change this point here and extend it down? Yeah, that's why they weren't exactly, because I needed to be able to move these around. So this is about 55 or 56 degrees, 156. That's our central angle. Well, we know our inscribed angle is going to be about half of that, which is around 78 degrees. And notice again, as I move this around, that angle does not change. As I go anywhere on this circle, the third vertice, it's still going to be half of the central angle. So if I move this value down here, see if I can get it to about 100 degrees. You can see how annoying that is, but yeah, it's close to 100 degrees. So the inscribed angle should be about half of that, which, as we notice, as I move this around anywhere on the circle, it's always going to remain exactly the same, even when they intersect, which is kind of cool. The inscribed angle and the central angle, even though they intersect here, are still going to be half. If we go on the inside, what happens here? Oh, well, then we get the 360 minus that value. But anyway, not that important. So that is properties of inscribed angles kind of demonstrated to you through GeoGebra. So we can also use tangents and right triangles to prove the sum of the interior angles of a triangle, which will be important for today's assignment. So if it is a tangent line, then it actually intersects, and the radius through the point of tangency intersects the tangent line at a right angle. So they're perpendicular to each other. So if I draw a line that's parallel to it, that goes through the center of the circle, it's also going to be perpendicular. Those two are alternate interior angles, right? So this is 90 degrees, so is this one up here, because we do have two parallel lines. We constructed it that way. Then if this is 50 degrees here, we know that the alternate interior angle of the 50 degrees is also going to be 50. All right, so the next question we might have is, what is the measurement of this angle right here? Well, that angle, because all of these have to add up to 180 degrees, can be found by taking the supplement of the sum of those two. So 50 plus 90 is going to be 140. We subtract that from 180, which is going to leave us with 40 degrees. So this angle here has to be 40 degrees. So these three add up to 180, but then we look and the same can be said for the angles of the triangle, right? Because they are the same as those two by the alternate interior angles. So 50, 40, and 90 are all going to add up to 180. So the sum of the interior angles of a triangle is 180 degrees, which we've seen that before when we did right triangle geometry. We're just proving it on a circle now. All right, then the Pythagorean theorem. So we're going to be doing math today. Our space math is going to be very closely related to this problem, so make sure we know how to do it. The first thing I want to point out is why is 4 and 4? Why are those two the same? Those red segment links there. So I can hear you screaming out from your phone. Apparently most of you guys are watching this on your phone, which is kind of funny. So 4 and 4 are going to be congruent because both of these are radiuses or radii. So the next question we have is, say this is a radius of, I don't know, the Earth, which is round. I know, flat earthers out there. Trigger warning. I know, I'll get better at that. So let's say that if the radius of the Earth was 4 units and we are 1 unit above the Earth, the question we have is how far can we see to the tangent line, or the horizon, in other words. So how far can we see this distance x here? Well, we can solve for that by using the Pythagorean theorem. So we set it up with our legs. 4 squared plus x squared is equal to 4 plus 1 squared. We can go ahead and evaluate the parts that we know. So 4 squared is 16, and then 4 plus 1 is 5. So when we square that, we get 25. Then we can subtract 16 from both sides, leaving us with 9. So x squared is equal to 9. How do we undo a square? Well, the inverse operation of a square is, or to the second power, is a square root. So we take the square root of both sides. So the square root of x squared, and we take the square root of 9, which leaves us with, that's funny, leaves us with x is equal to 3. So I made it a 3, 4, 5 Pythagorean, right, or Pythagorean triple, which makes it easy to do the math. But we'll be doing similar problems like this. We'll have decimals as answers because we're never going to get Pythagorean triples in the real world, but that's okay. So make sure you understand how to do this so that we can do our space math. All right, so the Pythagorean theorem is actually a conditional statement. It says that if it's a right triangle, then a squared plus b squared is equal to c squared. So the converse of that statement is like shoes on the wrong feet. Yeah, we're thinking converse. So if we know that the a squared plus b squared is equal to the c squared, then that tells us it has to be a right triangle. So we can prove whether or not this is a right triangle. Now, the other options is it might not be a triangle at all, or it could be an acute triangle or an obtuse triangle, but we don't need to get into that. We just want to know, is this a right triangle? And therefore, is this actually truly a tangent line? So does this actually only intersect in one point? So if they give us lengths of 3, 3, and 3 radical 2, you should automatically be thinking, that sounds kind of familiar, right? In fact, that sounds similar to 1, 1 radical 2, right? So that was absolutely terrible. Okay. You get the idea. So 1, 1 radical 2. So then what's the scale factor? If I'm going from 1 to 3, what am I multiplying by? Well, it's times 3, right? So 1 times 3 and radical 2 times 3. Yeah, so we know this has to be a right triangle because it is similar to 1, 1 radical 2, which is a 45, 45, 90 isosceles right triangle. So if it's similar to it, then, and this is a right triangle, then that means the corresponding angle also has to be 90 degrees. But how do we solve this problem with the Pythagorean converse? Well, we would do 3 squared plus 3 squared. Let me go back to this one right here. So 3 squared plus 3 squared is equal to, or some relationship to, 3 radical 2 squared. So that's going to be how we set this up here. I'm going to have to delete that, I think. I don't know quite how that's going to let me do it, but oh, that worked. Still figuring out all the tech stuff. Okay, cool. So 3 squared plus 3 squared is some relationship to 3 radical 2 squared. Well, 3 squared plus 3 squared is 9 plus 9, which is 18. But the next question is, how do we square a radical? So if you remember, squaring a radical is like multiplying it by itself. I'm just going to move this way out of the way. So 3 radical 2 squared is the same thing as 3 radical 2 times 3 radical 2. So then how do we multiply radicals with coefficients? Well, we break it down into 2 parts. So here we have 3 and 3. So 3 times 3 is 9. And then radical 2 times radical 2, which is just going to be radical 4 or just a regular 2. So 9 times 2, which is equal to 18. That was lovely. All right, so we had 18 over here, right? So we have the same 18 in both places. So 18 is going to end up being equal to 18. So if the a squared plus b squared was equal to the c squared, and it was, 18 is equal to 18, therefore it has to be a right triangle by the converse of Pythagorean theorem. And if this is a right triangle, that tells us that this green line here has to be a tangent line. So that's how our logic goes. First, the a squared plus the b squared was equal to the c squared, which meant that it was a right triangle. And if it's a right triangle, that means this is a right angle, and so it's a tangent line, which means it intersects the circle in only one point, even though it might be kind of hard to see if it did two or something like that. That's why we have to prove it. The only other thing I have for you for the homework is circumscribed figures. So this word circumscribed probably looks familiar to another word that you know. What were you thinking? I'm thinking circumference. Of course it's circumference. What were you thinking? Get your mind out of the gutter. Anyway, so what does it mean circumscribed? This word circum comes from, well, it's where we get the word circle, right? So it's to go around. So if we have a circle here, the triangle is going around or around the outside of the circle, just like the circumference is the distance all the way around a circle, right? And the other word you're thinking of, yeah, it means to go around something else, but that's entirely different. So if we have a circumscribed figure here, this triangle that goes around the outside, what we're doing is we're fitting a circle, an end circle, snugly inside this triangle. We actually did this in Unit 6, and it was pretty cool with the compasses and doing constructions. I think we used the medians. No, angle bisectors. So the angle bisectors, if we cut this angle in half here, that point of concurrency will give us the point of concurrency for the end circle. Then all we had to do was drop perpendiculars by using kites, properties of kites. That was fun. I wish we could do that again. Some of you guys probably don't. So if we look at this diagram here, we know the points through B and D are both tangent points, or points of tangency. So they're both perpendicular, right? So we got right angles there. And then if we draw this line AC, we have a right triangle, right? So this is a right triangle. The next question I would have is, what do we know about points BC, or segments BC and segment CD? Well, they're congruent to each other because they're both radiuses, right? So if those are both going to be radiuses, and then we know the angles are the same, and then what do we know about the segment AC? Well, AC is going to be congruent to itself because of the reflexive property, right? Things are congruent to itself. Remember the creepy baby photo, which I wish I had that cued? Darn. That would be really funny. But of course you remember the creepy baby photo. So then my next question is, what do we know about these two triangles? What do we know about the triangle, I'll call it triangle 1 up here, and triangle 2 down here? What do we know about those two triangles? Do they look like they're the same? And by the same, I mean congruent. Do they look like they're congruent? Yes, and they are congruent, but how do we prove it? Well, if we look here, we have the same congruent corresponding angles, the same sides here, and then the same side here. So what postulate are we using? Yeah, I know you remember this postulate. So this is actually the donkey postulate, or like what we like to call a money sign, money sign. So I can show you the diagram on this one. Actually, I'll slide to the right. Okay, so if we have this angle, and I use the money signs because this doesn't mean the naughty word. It means something else. I see it in rap tiles all the time. I still haven't figured out what it means, but they're not referring to the A word or anything. Of course not. All right, so this is the angle. Then we have a side and another side, right? But the donkey postulate, as we call it affectionately, is not going to be, it's not actually a postulate. It doesn't work. And the reason for that is if we have this angle, this side and this side, it's allowed to move. It's ambiguous. There's two different solutions. Are we talking about the obtuse triangle here, or are we using this side length and talking about the acute triangle? We don't really know. So the only way that the donkey postulate works is, of course, you remember, is if we have a right angle. And if we look at our original one here, a money sign, we do have a right angle. So we can use the donkey postulate, but we don't call it the donkey postulate or a money sign. We call it the hypotenuse leg theorem. And the reason it's called the hypotenuse leg theorem is because one of our sides because we have to have two adjacent sides, right? Angle and two adjacent sides. One of our sides is going to be a leg, and the other one would have to be the hypotenuse. So this is called the hypotenuse leg theorem, and it does work. So keep in mind, donkey postulate does not work, and again, we can't use that word in my class either, so it doesn't work. But of course, if you remember anything about geometry, I promise you guys are going to remember the donkey postulate. That's why I do it, because it's controversial, and it helps you remember. All right, so they are going to be congruent. Now, if they're congruent, then what do I know about this side AD and the side length AB here? How are those two related to each other? Well, they would have to be congruent by corresponding parts of congruent triangles. So when we have circumscribed figures, which is what we have here, again, because it's got an end circle and it's a geometric shape that goes around the outside. What's special about it is each one of these kind of little points or legs that come out from the tangent lines are going to be congruent, make two congruent triangles with the radiuses and the segment that goes through the center, right? And so that means that the corresponding parts are going to be congruent. So we can do the same thing just without loss of generality, the same proof up here. If I drew another radius, I know they're both right angles. This side in the middle is congruent. The radiuses are congruent. So donkey postulate, right? Hypotenuse leg, and so then we know that this is 7, and so the corresponding part over here also has to be 7. You know why that bothers me, but they need to be lined up. Same thing here, right? If this was 6, that would mean that this would have to be 6 down here. So you don't have to go through the rigor of proving this every time. I just want to prove it to you once so that you can see that's how we would solve that problem. You'll see that on the homework as well. So speaking of the homework, let's look at number 1. So I'm assuming that you've printed off the assignment. Some of you guys have been turning in the assignments. You don't actually have to turn them in at this time because you can grade them yourself. So there's really no reason for that. If you want to turn them in just to show me that you're doing your work, I appreciate it. And it does feel good to know that you guys are actually doing your work and you're watching the videos. So thank you for that. It helps me want to work hard for you guys because I know that you're still engaged in learning. So thank you for that. But you don't have to go through the effort of uploading them if it's a hassle for you. Some of you guys have been marking up the PDFs, I suppose, on your phone, because about 78% of you guys are watching all these videos from your phone. Maybe you just have that in the background, with, watching it while you have you're working on it on a computer or an iPad or something like that, or some tablet. But anyway, you guys are doing great solving all the tech issues on your own and being innovative. And I'm doing my best on my part, so I appreciate that. So if you have access to a printer, you're probably going to want to print it out. That's the easiest, but if not, whatever you guys are doing, or copying it on a sheet of paper, which is super old school, that works too. All right, so on this diagram, we have two tangent lines. They also tell us to assume that if it looks like it's a tangent, that it is a tangent. So we don't actually have to go through the rigor of proving that on some of the problems. It'll just be an assumption. So we got two tangent lines, which we know are 90 degrees, right? So up here we have 90 degrees, and down here we also have 90 degrees. Then they tell us that this angle out here is 40 degrees. So our question is, what is the central angle going to be? So how are we going to solve this problem? What do we notice about this shape? How many sides does it have? We got 1, 2, 3, 4. So this is a quadrilateral. What do we know of the sum of the interior angles of a quadrilateral? What do they add up to? Well, they add up to 360 degrees, right? Remember our formula? N minus 2 times 180 degrees. So the number of triangles times the sum of the interior angles of each triangle. So that'll give us the sum of the interior angles of a polygon for any n number of sides, right? So we did that unit. Hopefully you still remember that. But anyway, easy stuff, just 360 degrees. So all we have to do now is just plug it into our calculator, unless you can do it in your head, which is totally fine. So we're going to add them together. We're going to do 90 plus 90. And then we're going to add 40 to that. And I'm going to subtract that value from 360, which leaves us with 140 degrees. So the measurement of the central angle is going to be 140 degrees. All right, on number 2, so we have a triangle this time, so the angles add up to 180. If we have 90 down here, because this is a tangent line, and this is 51, we can find the missing angle by subtracting from 180 with the supplement of the whole thing, or just finding the complement of 51, because if this is 90, the other two angles have to add up to 90 as well. So that would leave us with 90 minus 51, which is just 39 degrees. So if you can do it in your head, that's totally fine. And by the way, you've got your answer bank on the side, so you can be marking these off as you go as well. I just didn't show it on the assignment. or on the presentation here. All right, number 7, we want to know, given these measurements, does this make a tangent line? Is this a right angle? So we're going to use the converse of the Pythagorean theorem. So when we set that up, you have to do this freehand, but we're going to have 3 squared plus our other leg of 3 radical 3 squared. And we want to know, how does that relate to 6 squared? And now if it's equal, then that would mean that it's a right triangle. But if it's anything but equal, then it's not a right triangle. And therefore, this is not actually truly a tangent line, and they would have to be a secant line. All right, so to find those values out, we can plug it in your calculator, or you can actually do this by hand or in your head. So 3 squared is 9, right? 3 radical 3, remember, that's going to be 3 radical 3 times 3 radical 3, because when we square something, we're multiplying it by itself. So 3 times 3 is 9. Radical 3 times radical 3 is regular 3. So 3 times 9 is 27. So that's going to be 9 plus 27, or 4 times 9, another way of doing that. But adding those together, which would give us 36. And 36 is what relationship to 6 squared, which is also 36? They're equal. So if those two are equal, what do we know about the triangle? It's a right triangle. And if it's a right triangle, what do we know about this line up here? So if this is truly a right triangle, then that tells us that this has to be a tangent line. So that's a point of tangency. All right, so our answer would be yes, it's a right triangle. All right, number 12 is very similar, but this time notice they're giving us this 4, which is the extension. It's the part outside, right? So what we need to know, first of all, is what is the length of this radius here? Well, how are we going to find the length of the radius? Well, it's congruent to that radius, right? So it would have to be 6. So our values are 6, 8, and then when we add these two together, the whole hypotenuse is 10. So this is a Pythagorean triple. You probably might recognize it, but 6 squared plus 8 squared is some relationship to 10 squared. And that's going to be 36 and 64. When we add them together is 100. And 100, sure enough, is equal to 10 squared of 100. So that tells us this is a right triangle. And so therefore, yes, this is a tangent line. Number 10, similar problem. We have a radius of 9, so this one's 9 here. We add that to the extension, which is going to give us 15, and that's another Pythagorean triple. So we have 9 squared plus 12 squared is some relationship to 15 squared. 9 squared plus 15 or 12 squared is going to be 225. Again, we can just plug that in the calculator if you like, if you're not sure about that. I just know what these answers are off the top of my head because I wrote the assignments. All right, so we can do 9 squared plus 12 squared. Okay, and then we're going to check that to 15 squared, which is also 225. Okay, so those are equal, so it's a right triangle, just like we thought it was. So 225 is equal to 225. So therefore, this is a right triangle, which means that it has to be a tangent line. All right, 13. I think this is the last one I'm going to do with you until then we're going to do our space math. And I'm going to break the space math into a separate video just so I can show it to other people without showing them all the tangent line stuff that comes before it. I think that would be kind of fun. All right, so on this one we have a circumscribed figure, right? Because it goes all the way around. The circle is an end circle. It goes on the inside and fits snugly on the inside of our polygon, forming tangent lines, right? Or tangents, points of tangencies. So what we know is that if this is 3 up here, that means this part here also has to be 3. I wonder if I duplicated it. That would be nice. No, I didn't. I didn't. Okay, so anyway, if that's 3, it means the other one also has to be 3. If this is 17, that means this also has to be 17. If that's 7, this one has to be 7 as well. If that's 8, this one has to be 8 as well. Lovely, 8. All right, so the question, I believe, asks, what is the perimeter? So the perimeter is going to be the distance all the way around. So add them all together. A trick you can do is just add one of them. So 3 and 17 is 20, right? So these two add up to 20. And then 8 and 7 adds up to 15. Now we only did this 8, this 7, this 3, and this 17, which would give us 35, right? So if I add those together, it gives me 35. But what do I have over here? I have another 3 that wasn't counted, another 8 that wasn't counted, another 7 that wasn't counted, and another 17 that wasn't counted. So all I have to do is take the 35 and multiply it by 2, which will give me 70. So 70 units. So our perimeter of our circumscribed quadrilateral is going to be 70 units. Now, if you don't like that trick, it's okay. Just find out what each one of the links are and then add them all together, or you can add one of them and double it like I did. Either way. All right, so that's it for the assignment, the front side. We're going to do the back side together, but I'm going to break that out to a separate video, so it'll upload shortly after I do the first one. So I will see you in just a little bit for the back side. Space math. I know you guys are excited.